Hello, fellow humans. We talked a little bit about Kingda in class, which is a roller coaster in New Jersey that is still the tallest roller coaster and has quite some fast speeds at the beginning as a launched roller coaster. We went through the first acceleration in class, but I thought I'd go ahead and go through a different part of the roller coaster acceleration to help us to understand more about this kind of how do you calculate acceleration when we're talking about vectors as a whole. So what I have my cart in two different positions in time, 2 seconds apart from each other. Where starting off at the bottom, we've got this car here that has a starting velocity. It was launched, and its velocity along the track here is 57 meters per second. That's after the launch as it's moving along. But as it moves along the track, it eventually comes to this point where it is now heading upwards, like straight up. And it ends up going a velocity upwards of 52 meters per second. And I know that it's 52 meters per second upwards because every single item that you throw, in order to get it to the height of the top of the track of 139 meters, has to be moving at 52 meters per second or faster if there's friction involved. So it's at least 52, and it might be up to 57, but it will probably have lost a little bit in the transition from one place to the other. So let's look at this as a whole. If we're thinking about acceleration, acceleration is equal to a change in velocity over a change in time. And my change in velocity means that I need to take my final velocity and subtract my initial velocity from it, and then divide by the amount of time that it takes for that to happen. Now, you might say to yourself, oh, this is easy. It's 52 here and 57 there, and this is my final velocity up here at the top, right? VF is here, and this is VI right here. So 52 minus 57, but that doesn't work that way. When we're dealing with things pointing in different directions, we have to deal with the vector quantities themselves, not just the magnitude of them. So we need the direction too. So I'm going to start by putting in my final velocity, and that final velocity is here, going kind of straight up here.
It's new.
And that final velocity going straight up is 52 meters per second. And then my velocity 57, I need to subtract it, right? And if I'm going to subtract my final velocity, I need to realize, how do I subtract vectors? And the answer is you just turn it around and then add it like we normally would. So it's 57 to the right. So now it's going to be 57 to the left. And I'm going to place that nose to tail, just like we've learned here. And so I'm going to put in my 57 right in here. So this is 57 meters per second. And my change in velocity then is going to be nothing more than here at the tail and going up to the head over here. So that's my change in velocity. I have the direction already, and I have the magnitude by length of the arrow, but I can actually solve for the numerical length as well by using a handy dandy little tool, because this is a right triangle. And my handy dandy tool is the Pythagorean theorem, which is a squared plus b squared equals c squared. And I can use that to find out whatever this length of the triangle is. So plugging in the things that I know, I can say 57 squared plus 52 squared is equal to c squared. And if I square this and square that and I add them together, I get 5,953 is equal to c squared. And if I solve this, I need to take the square root of that number, 5,953. And what I get is 77. And this is 77 meters per second. This is my change, right, in velocity, right? So this number up here, this leg length of the triangle, which is my change in velocity, is 77 meters per second. Nice. Now you'll also notice that I've got a direction, which means that my acceleration up here is kind of in this direction, if I want to think about it, and it's a 77 meters per second. Now I'm dropping in an A here because if I divide by time time has no direction, and so I can know that my direction is always going to be that one, whether it's the change in velocity or the change in time, or excuse me, or the acceleration. So down here, I'm going to go ahead and solve this by taking this 77, which is my change in velocity here, and that's meters per second, and I'm going to divide that by my amount of time, and my time is up here at the top at 2 seconds, so 2 seconds, which gives me a final answer of 77 divided by 2, which is 38. This is 38 meters per second squared, or meters per second, same idea. So this is my final answer as to the amount of acceleration that is felt in this transition from going straight up or straight out to straight up. Now, in terms of gravity, right, the acceleration due to gravity, the G, right, is equal to 9.8 meters per second. This is what you feel, that you feel all the time because of gravity. And we can talk about G-force. G-force is the feeling you get because of this acceleration. Notice the relationship between these. This is 38 meters per second squared, and what you feel normally on the ground is 9.8 meters per second squared as my acceleration, which means that this is about, not quite, but about 4 times greater down here. And 4 times greater means that's a significant amount of force that you would feel, recognizing that as 4 times the amount of acceleration that we get into it. The human body can, normal kind of human body can feel comfortable. Well, maybe I shouldn't say comfortable. Can withstand is a better way to say that. About 5 times the acceleration due to gravity here. And this one is giving you 4 times. So this is a pretty significant roller coaster change here, not for the faint of heart. All right, ladies and gentlemen, I hope that was helpful, and I will see you in the next one. Adios.